Hello, everyone. We will be starting in approximately a minute or two. Alrighty. Hello, everyone. I'll start off our program today by introducing myself. My name is Deirdre. I'm based in Santa Barbara, California, and I work as the Engagement, Outreach, and Partnership Liaison for Protected Seas. In my work, I routinely connect with marine scientists, MPA practitioners, national and international policymakers, and the conservation community. I encourage broad usage of the Protected Seas Navigator data to streamline and inform marine spatial planning and various other assessments. Protected Seas has developed the most comprehensive platform for assessing global regulations. We have data in 200 countries in 20,000 marine areas with translations in 47 languages. And if you'd like more about that tool, I'm easily found on LinkedIn, and I can drop my contact information in the chat if you want more detail. So with that introduction out of the way, let's kick it off. Welcome, everyone. Now that you know who I am, I would love to hear or see who's on the call today. So let's all just take a moment to arrive here at our webinar and put a shout out with your name and where you're zooming in from on the chat. So welcome, welcome. And I'll say too that we're really delighted to have so many countries represented today. We have more than 20, including Algeria, Australia, Bangladesh, Canada, Chile, China, Cyprus, Georgia, Germany, Haiti, India, Kenya, Mexico, Nigeria, Portugal, Somalia, South Africa, Spain, the United Kingdom, and the US. That sounds like a lot of interest in Kate's talk. So without further introduction, let me introduce her now. Also, I'll mention too that this is always available on the YouTube recording after, so you can always see it there. So Kate is employed by the Mississippi University's Northern Gulf Institute, which is a cooperative institute for NOAA. Kate's background is in coastal and delta geology, and she's been working at the institute for nearly a decade and a half. Her current role involves GIS mapping for various datasets to support restoration efforts in the Gulf of Mexico. And today, Kate will be discussing the Coastal and Marine Ecological Classification Standard, which is a comprehensive classification scheme for marine and estuarine environments. And she'll tell you all about that, but by way of a quick explanation definition, that tool provides a common language and data classification framework that enables consistent and comprehensive ecological characterizations across a complete continuum of the aquatic system, from coastal zones to the depths of the ocean. And this approach can be universally applied to all types of data and has been used, again, for over a decade by individual projects and programs in the United States to meet various objectives. And as you can imagine, This standardization leads to a greater accuracy and understanding of these aquatic systems. So with that, Kate, please take it away. And I do have some links to your work and projects, and I can drop those in the chat as well. Thank you.
Thank you, Deirdre, and thank you everyone for coming this morning. I will go ahead and share my screen and get started. Can everybody see my screen now and see the slides? I'll just hide this stop sharing as well. Does everything look good?
It does, Kate. Thank you.
Oh, thank you. Great. All right. Well, thank you and good morning. And thanks again for coming. My name is Kate Rose. As Deirdre said, I'm with the Northern Gulf Institute at Mississippi State University. We're funded by the NOAA National Centers for Environmental Information. And so today I'd like to introduce you to CMECS and what it is and how it's used. And also to talk a little bit about our alignment with the Marine Life 2030 program and how we'd like to continue to network with the Ocean Decade efforts. So a quick introduction. So CMECS is a common language for interpreting data. And it's a catalog of defined terms, which we refer to as ecological units. And so these are used for annotating observational data in coastal, marine, and lacustrine habitats. Its domain is U.S. waters, although it has been applied outside of the U.S. and definitely applies to many environments outside of the U.S. But we focus on U.S. waters, ranging from the tidal splash zone of coasts and intertidal euhaline and brackish wetlands, and the waters of the Great Lakes as well. We don't forget our interior waterways, and all the way down to the depths of the ocean. And it's built on existing classification approaches and vocabularies, but they're united within a single scheme to be able to provide that continuity of standardization and classification. CMECS is also technology agnostic and scale independent. I'll talk a bit about that later. And the units are organized in a component-based semi-hierarchical framework, and this is helpful for how it organizes information and allows supports mapping and synthesizing information. CMECS also includes a set of modifiers. And so modifiers are additional descriptors, and those can be optionally applied to units to provide more detail. And this allows a little bit of more customization and flexibility in how people use CMECS. So CMECS was first endorsed as the National Ecological Classification Standard and published by the U.S. Federal Geographic Data Committee in 2012. And so this development was funded by NOAA, the Office for Coastal Management, or OCM, in partnership with the NGO NatureServe. And it was led by members from several U.S. federal agencies. But it was co-designed by coastal and marine habitat experts from federal, state, local governments, academia, NGOs, and industry partners in the United States, Canada, Australia, and several European countries. So it was quite of an extensive effort. There had been input from over 100 contributors, and it was put out for a 100-day public comment period, and comments were addressed. And went through several versions and test iterations before it was finally published. And so CMECS was designed and reviewed to be updated over time. Oh, and I think I wanted to add, just to emphasize what a huge effort this is, I think that the scoping for this started in about like 1998 or so, just to be able to continue planning and putting all this together. So it has been a very big effort, and took a lot of work on behalf of all of the authors and the contributors. So the ultimate goal of CMECS, though, is to facilitate assessment and monitoring, protection and restoration, and management of biotic assemblages, and harvested species and protected species, vital habitats, and important ecosystem components. And by providing this common language, and providing a language for translating data into human understandable terms, this enhances scientific understanding and advances ecosystem-based and place-based resource management, and helps us to safeguard coastal communities. There's more about this in the standard document itself, which I have a link to down there at the bottom of this slide here. And so the CMECS implementation group, so CMECS is currently maintained and supported by this CMECS implementation group. And so this is just a small group, basically, and the members include many of the original CMECS development team. I've listed here some of the core members who have been providing governance and expertise on the update work that we're currently doing. And so I'll describe more of that later. But basically, anyone who has experience with CMECS can join. It's mostly a voluntary effort. And what we aim to do is to promote and provide guidance for the use of CMECS. And we're coordinating the standard maintenance and the updates. We also facilitate working relationships between CMECS users. So we try to spread information and help people share their work as much as possible. You can contact us via email with any questions that you might have. And we also maintain 2 websites that have more information. The one over on the left there is on the Interagency Ocean and Coastal Mapping Coordination Team's website, and that focuses on general information and guidance. Over on the right, the site on the NOAA National Centers for Environmental Information, or NCI website, it focuses on the CMECS catalog and vocabulary maintenance. And I think everyone here is probably familiar with the UN Ocean Decade, but I did want to include this slide with the vision statement and framework, and the website with the link for more information if this is new to you or if you need to find out more about it. And so with CMECS, we thought we would contribute mostly to a couple of these challenges, mostly challenge 2, to help protect and restore ecosystems and biodiversity. And since we have so many projects that use CMECS, and many of those are conducted for that goal. And then also we thought we would apply to, or can help with challenge 9, supporting skills, knowledge, and technology for all. So we're in the process anyway of doing a technological update to CMECS resources. We're learning more about the new and novel ways that people are using CMECS, and doing this digital transformation is helping us to make it more accessible to people and more accessible to new technologies and applications. And so we applied last year to the Marine Life 2030 program. And so CMECS is now an affiliated project there. And so this is the Marine Life vision statement here as well. And so we'd like to work with them to sort of help to leverage emerging innovation and integrate biodiversity into a global ocean observation system. And we can see here that we have a common theme here where we're trying to establish and promote interoperable standards, right? So, and we also want to be able to apply enhanced knowledge of marine life to co-develop solutions. So by joining Marine Life 2030, we're really hoping that we can connect with other information and knowledge building resources so that we can help to provide compatibility between them. And so we sort of have like a basic project plan sort of outlining a couple of tasks that are applying to this. So the first part I've mentioned a little bit is the CMECS scientific content, the updates, which we refer to as the dynamic standard process, because CMECS was developed as a dynamic standard. And so we're conducting the first comprehensive review of CMECS since its publication. And that's basically just holding a series of virtual work groups made up of scientific subject matter experts. And we're reviewing a lot of the feedback that we've been getting from the user community since it's been published. And so we are taking those recommendations and making a few changes where necessary, and improvements overall to help keep CMECS current and relevant. And so as the outcome of that, our CMECS units in the framework are updated, and we aim to publish and distribute updated resources such as work group reports and an updated CMECS catalog. And this work is coordinated by the CMECS implementation group. And then in the light blue box here is work that we're doing mostly with a lot of contributions and help from the Earth Science Information Partners community. I work with the semantic harmonization group, who have been really helpful in helping me understand how to do this technological transformation and the various tools out there to use. So I'm deeply in debt to those guys. So basically, we're or have completed already is serialization of CMECS into a resource description framework and web ontology language formatted semantic resource. So an OWL is an OWL flavored ontology, and enhancing CMECS with persistent unique identifiers for each unit. And we're providing clear provenance and linkages to sources. And hopefully over time, we can build in alternate terms from different languages and cultures, because a lot of people refer to the same thing by a different name. And to be able to do that translation, this provides the capability to do that. And then we're also curious to see how CMECS compares with other ocean and marine data resources. I don't know if anybody here is familiar with the environmental ontology, which is ENVO, or semantic web for Earth environmental terminology suite. And those have been around for a while. And so we're sort of performing a little bit of harmonization work, comparing what terms each of these ontologies have, and do we define things the same way? If we don't, how do we disambiguate those, the meanings and clarification, and that sort of work. So, and then I did want to also just, this is maybe a little bit repetitive here, but just to acknowledge, the Vision 2030 white papers that were published, and I think Marine Life was deeply involved in the Challenge 2 paper. And again, trying to laying out the issues of how we need to work on interoperability of observations, and increase collaboration and connectivity between marine life databases, work to make data interoperable and comparable spatially and temporally. And also to try to incorporate knowledge on biodiversity and ecosystem change. And so, I was really targeting here this key recommendation to also support existing networks for biodiversity observations. And so the ones that are listed here, these would be like in addition to the other resources that I just mentioned, the ENVO and Suite, but to see how we can, take this terminology and this ontology and help enrich and support databases like OBIS, which I'll talk about a little bit later, and others. So why standardize? I think that, I've said, this has been said already, I think in the introduction, but why do we want to do this? And just simply because standardization reduces ambiguity of meaning, it provides consistency and allows for interoperability, and it facilitates the sharing and use of data across domains and across communities. And so we can see from the cartoon there that without clear definitions and terminology, things can become very confusing. And so standardization leads to greater accuracy in data discovery and databases and repositories, and it leads to efficiencies in data analysis and synthesis for large data sets, machine learning applications, and it can facilitate interdisciplinary research. So the overall goal is to develop a process and create data sets and products that can serve a variety of purposes. And so we ascribe to the saying that map once, used many times. So as part of that, we've got two sort of, in relating to CMECS and the work that we're doing with CMECS, we're working on, or we have a standardized interpretation of data. So CMECS is terminology that allows you to apply consistent terminology to data, but we're also working on standardizing the format that we deliver that information in. And so I'll talk a little bit later also about the FAIR vocabulary and making it open source and machine actionable. And so how is CMECS used? I'm bringing this graphic up again. It's just a helpful reference point, but it's not only used in GIS mapping, but it is used for that a lot. So it's so the structure of CMECS sort of emulates the concepts of GIS, where we have different components, and so you can sort of envision these as different GIS layers. So each setting and component contains a set of defined terms, and these can be mapped or combined. And each unit is meant to represent a measurable space. And so it can be ascribed also to a geographic area. It's something that can exist within a specific location. So this is why it's very helpful. So you have your data that is collected at a certain point, and so you have a unit that can represent that in space. Each setting and component contains units, and they are hierarchically nested, and they range from general to specific in both spatial resolution and in conceptually. And as I said before, we've got the modifier units. Those are additional descriptors. And if you combine all the components together, these are all the abiotic features in an environment. Combine them with an associated species to create biotopes. Again, I'll talk more about that later too. Also, I had mentioned earlier that it is sensor independent. And so I'm showing this table here that is that was created by one of our implementation group members for a paper on benthic habitat mapping at Fire Island National Seashore in New York after Hurricane Sandy, where they were doing a comprehensive benthic habitat survey. And so they collected, so you can see up at the top here, we've got the different types of data for remote sensing. They collected bathymetry data with LiDAR, multi-beam echo sounder, and multi-phase echo sounder. They got backscatter, side scan, and aerial imagery. And to those, down at the bottom, they were able to apply the geoform component, substrate, biotic component, and modifiers to that to develop a data product. And then for imagery, they took still photos and video using drop camera, towed sled, AUV, ROV. They used SPI or sediment profile imagery and aerial imagery. So again, they were able to use the geoform, substrate, biotic component, and modifiers. And they also took ground truthing grab samples, so sediment cores. And for that, they were able to use the substrate component, biotic component, and the modifiers. And so this is perhaps the hierarchical nature of the classification is maybe most easily illustrated with the substrate component. So the substrate component units describe the non-living material that forms the surface of the aquatic bottom. It's not a geological classification. We're not really concerned with the geological composition or origin or the specific like mineralogy of the substrate, but more concerned with whether it's consolidated or unconsolidated and the size and mixture of that substrate, because these are the factors that most affect use by biota. So CMECS also limits our classification to the upper 15 centimeters of unconsolidated sediment, and focusing on the materials that provide a surface for growth of attached fauna or burrowing fauna, actually. So within the substrate component, there are three origins. We have a geologic substrate, biogenic substrate, and anthropogenic substrate. And then within each of those origins, now there's a set of units that are hierarchically organized. And so I've just sort of picked these out to sort of identify what we see in the photos there. So for the geologic substrate, there we're seeing this class that the broadest category there is coarse unconsolidated mineral substrate. But we can also see that there are distinct rocks or boulders, and we can't really tell what size they are actually, because we don't have a measurement here. But that's definitely possible to do. There are established methodologies for doing that. But so the next level down would be just a general subclass where we would call it gravel substrate, and we use the Wentworth and Folk classifications, which are well-established geological sedimentology classifications, and those define gravel substrate as anything ranging from 2 millimeters to less than 4 meters, basically. So that's a very broad class, and it may well be that in your data, whatever it is, whether you're looking at an image or whatever, that's the most information that you have, and so that's a very broad category that you can use. So in CMECS, the general rule, though, is to classify to the lowest level that your data supports. So here we can see that we could actually, there are some fragments that are particles that are probably that big. So you might have some that are gravel substrate, but we can also see that there are some that are smaller. So they may be very coarse gravel, which would be the next level down at the group. And those are 64 millimeters to less than 4 meters. And to go even finer to a subgroup boulder, again, with a more specific particle size there. So that is descending in order from more coarse to finer size categories. And then looking at the biogenic substrate, I think the image there is showing a lot of like mussel shells and bits of rubble from consolidated mussel shells, cemented mussel shells. So within the biogenic substrate, again, so this is non-living material that was formerly alive. So the coarsest class is coarse unconsolidated biogenic substrate. The next level down would be biogenic rubble. The next level down would be shell rubble. So you could just use that if you weren't able to discern what type of shell it was. You could just stop right there. Those have the same size categories. However, if you can identify that it is mussel, you'd go down to the subgroup, the lowest level of the classification, because that's indicating the more specific origin type. And so again, with the anthropogenic substrate, we're looking at some relict pilings, I believe they're a bit encrusted. And so that's in a class called fixed anthropogenic substrate. And you could stop there if you didn't know what was actually composed of, but you can also go further to call it fixed anthropogenic wood substrate, and then down to the group, which is pilings. And those are all, again, the same size category, but becoming more specific in origin composition as you go down through the hierarchy. So, there are many more units there, but that gives you an idea of the hierarchical framework of the classification. And so, as I mentioned, there are also optional modifiers, and so that you could apply to substrate classifications if you wanted. We have anthropogenic impact and ARPD and RPD depth. You could apply benthic depth zones to these, the co-occurring elements. So for a situation, like that anthropogenic substrate, where you have image over there, where you actually have some mineral substrate there, along with your anthropogenic, and there's a way that you can combine those into co-occurring elements for more complex classification. We've got, and I won't read through all of these, but we have many substrate descriptors and surface patterns and things like that you could apply to whatever situation your project needs. And so what does this look like once you figure out what you have and you map it out? Here are a couple of examples. You could do something like just apply it to various points and have a point map, right? So like the one on the left here. I know it's a little hard to read that legend, but so for each point is assigned the dominant substrate type at that point, whether it's gravel or sandy silt or muddy sand, slightly gravelly mud, and so forth. And so you could just leave it at that point map. Over here on the right, again, I'm showing an image from this benthic habitat mapping at Fire Island National Seashore, where the substrate information has been combined with the geoform combination to give an overall geologic classification of that site. Where you can see in that legend, you have we have lagoons and a surge platform and a dredge channel, but then also describing the type of sediment within those geoforms. So you can see that there's a lagoon for a sand plat, and it's composed of medium to fine sand, and the percentage of that coverage there. So then also we'd like to let you know about the CMECS settings. So these are also not usually applied to all projects, but they are helpful for aggregating information into sort of like a global context, global and regional contexts. And so the biogeographic setting that CMECS uses, they simply adopt the Spalding marine ecoregions of the world, MEOW, which are also pretty widely used. And then we also have an aquatic setting, and that's based on FGDC wetlands classification on their system and subsystem levels. And so that also sort of lets you aggregate information, whether if you had substrate information or biota information, to aggregate those into specific classes that are defined, by levels of salinity and photic and other other physiographic characteristics. And so we have, as I've mentioned, a lot of people who use CMECS, and so CMECS aims to be flexible enough for people to use it for whatever their needs are. And so individual projects have their own approaches to mapping and to using it. So there is no prescribed or defined way that it must be used, other than, a few certain guidelines of, how things might apply. But there can be a lot of customization of CMECS for different projects, but ultimately, when you get down to the actual, you'll always be able to look at a classification and identify the different units and be able to see what those units are, because all the units are defined. So you'll be able to have like a precise definition for what is actually making up the overall description of the project. So we stood up a little web map application, and this is just sort of like an informative product where we have points on the map that just show the locations of different projects, and the pop-ups kind of have links in them to more information about the project, so people can explore to see what's been done in a certain area, and go to the producer's website or paper and learn more about the work that has been done there. So that's something that people can explore on your own. I've just sort of highlighted a few of the different projects there. There's quite a range of applications. And so I'll show some specific examples now. So the Bureau of Ocean Energy Management is a U.S. agency that surveys and collects data to identify sediment resources in the U.S. EEZ. And so they use the CMECS classification in their data collection, along with other non-CMECS attributes that are geologically based. But because BOEM often contracts out their data collection surveys to private companies or universities, having a standard set of variables to work from helps them set requirements for deliverables and to make sure that their products are consistent from survey to survey. This is a favorite example of mine. I really like this application of CMECS. Here they've used the biotic They've used both the biotic component and the aquatic settings and some substrate, even though the substrate's not really showing up on here. But so what they have done is taken like new and existing data, the existing data they've crosswalked into a CMECS classification, added new data into the classification. And so this is an effort between 3 states on the West Coast of the United States, between Washington, Oregon, and California, and involved like a consortium of different players from like universities and state agencies and so forth, and it gives everybody sort of like this common operating picture for either collecting new data or for classifying the data, and to be able to pull all of that together to have consistent categories of habitat types. And that allows you to quantify the area of each habitat type so that you can get a full picture within this along the entire coastline of the West Coast, to help identify, which areas need protecting, which areas need restoring, which are healthy, which are increasing in area, which are decreasing in area, and to be able to do a whole lot of prioritization work for how these habitats are managed by across all the states. And so the image on the right is just showing the initial view of the map viewer. Those circles indicate where there are the number of different estuaries within there, but you can drill down. And so I've sort of superimposed this inset here of the Columbia River, and there you get like a pop-up with a bunch of information, and you can see the map over on the right with the different habitats that are identified there within that boundary. So that's a really great example of how standardization can really help people and work together and bring information together for useful purposes. And I'd also like to highlight the Esri Ecological Marine Units. This was a project that was done by, led by Esri, using Esri software, but involved a whole lot of other subject matter experts to pull this together. And so what they did was they took the global gridded data set, oceanographic data set, which was the NOAA World Ocean Atlas. And so those are measurements of ocean variables throughout the water column, from the surface, sea surface, to the sea floor, and classified them with CMECS, but also some other classification variables that aren't in CMECS right now. So the variables at each point are classified with this descriptive terms. So, and then when you click on a point, which I hope you can see over there on the right, it's a very difficult viewer to get a good screenshot of. But I've also put the link down there to the application, which is really interesting to be able to like navigate and play around with. So when you click on a point, it'll show the temperature, salinity, dissolved oxygen, also like other variables, the profile data for those, with the depth and the thickness of the layers. But because of the CMECS classification, terms appear up at the top of that EMU box there. So instead of having to describe something in, oh, we've got like at this point, it's, this range of salinity, we can use terms like, the water's mesopelagic, or it's cold, it's euhaline, severely hypoxic. And so this is like human understandable language that makes it much easier to communicate the conditions than simply using the actual data itself or data classes. So then there's the point data, and then I've also included, I guess, that reference to the accompanying publication, because you can then use that tool to generate 2D maps at different slices throughout the depths. And so it's a really neat product, and I think provides a really good way forward to looking at how to combine data in a global setting. And so moving away from strictly mapping per se, but another application, this is used by the NOAA Ocean Exploration Program. And so these are the NOAA research ships that go out and they map, perform mapping campaigns and, collect data, from using collect bathymetry data as well as like water column data, oceanographic data, by collecting in situ samples. But they also have now like a growing fleet of rovers, right? So that they send down like these AVs and record video to be able to ground truth the biology down on the seafloor and in the water column. And so as they're running these videos, they're using a program developed by Ocean Networks Canada. It's called CTube. And so that allows you to sort of like view the video as it's going along. And then they have scientists you can call in and like in real time annotate the video with the different organisms. So, but they also realize, or rather than just collecting and identifying the different like corals and other fauna that exist in the seafloor, that they also wanted to document the environmental variables. So you can see over there on the bottom right, there's a annotation entry where they can tag the video with the substrate type or geoform that they're looking at in the video as well. And so, when you end up with hours and hours of video, it's this allows people to go in and sort of search for an annotation and then go and find the exact frame or set of frames that they're looking for. So it's been useful in that regard to help people search this vast collection of video data. But they're also now using sort of like these video tags and because the human annotation can be very like tedious and time consuming, especially, when the submersible is out there for hours and hours, to be able to sit there and try to consistently take an annotation, at a specific every like at a specific time interval over time, so that they're looking at using these tags and the existing video to train machine learning algorithms to be able to go through and then take those tags and be able to then automatically identify further in the video. So that's a new use that's happening with video data. And another application also now related to the deep benthos, the NOAA Fisheries Mesophotic and Deep Benthic Communities Restoration, or MDBC project. And so this is a project that is funded by restoration funds from the Deepwater Horizon oil spill incident that happened in the Gulf of Mexico. And so these are a set of 4 different projects to restore mesophotic and deep benthic habitats. And it consists of 4 separate projects interrelated. The first is mapping and habitat modeling, where they've gone out and mapped the target areas to get really specific habitat information so that they can see what the habitat is existing right there, and to document any like biota that exists right there, and to take that information and to model suitable habitat for different coral species. And then they're taking that information so to determine good sites for transplanting coral. And so that's part of the second project there, where they're propagating coral samples in labs and taking them down to those identified suitable habitat sites to see if they can propagate the coral there and help regrow, jumpstart recovery in those areas. So they use CMECS when they're classifying the data to map and in their habitat modeling. And also, they'll be going back and doing further habitat assessments, and we'll use CMECS for that as well. And so I'm going to end this whole set of projects on this one here to be able to talk about, I've got circled here, the biotopes, because that helps me sort of transition into the next part of this. So this is another really great application from the West Coast. This is a survey or project for the state of California doing some offshore siting for wind energy management projects. So the first step in doing this is to go out and do a comprehensive benthic habitat survey and geologic surveys. And so what this team has done is go out and collect substrate data, backscatter data to determine where there's like hard and soft sediment, and bathymetry data to identify different geoforms and landforms on the seabed, as well as document like any biota. And so then they've gone and taken that extra step to combine these together into, I think over here, you can see the CMECS description on the right-hand side. So they haven't incorporated really like any water column data. So it's not really like a full biotope, but you can see how we're beginning to make these associations of the biota with the environment. So there are classes that are, sea star on soft substrate, and brittle star on mixed substrate, and things like that. So so beginning to make the associations, the associated species, tying the associated species to the habitat which they live in. And so those are called biotopes. And so I wanted to take that example and sort of compare and contrast it with other existing classification schemes. And so these are ones that probably many people are familiar with. They've been in use for a very long time. And indeed, CMECS reviewed both of these classifications extensively when they were going through the CMECS development. So the one on the left here is published by the Joint Nature Conservation Committee, or JNCC, and it's the Marine Habitat Classification for Britain and Ireland, and also UNIS. And so these two are focused on providing maps of biotopes in their environments. And so I've gotten a screen grab here on the left of the JNCC vocabulary. And so it is also like hierarchically based, but you can see how it's much more specific, and all of these environmental characteristics are sort of hard-coded into the descriptions, right? So you end up with, at the very like lowest level, things like mytilus and barnacles on very exposed ulitteral rock, right? And so that's a very specific, it's a very specific unit. And so UNIS uses the same approach, and indeed they, share and they coordinate with each other, right? So, and this is like a very useful way of monitoring biodiversity, because you do have that biotic information mapped out, because we do want to see ultimately, right, the distribution of species in the environment. But CMECS purposely, took a different, somewhat of a different route with this. And so even though with CMECS, you can choose to develop a biotope, right? But CMECS wanted to provide more flexibility, simply because, if they're recognizing the fact that, that a biotope, there may not be biotopes for all, or there aren't biotopes for probably for every environment on the Earth. And also simply having a species association, we use biotic communities that we, in CMECS, that we associate with the habitat. But simply because you have a biotic community present doesn't mean, in a certain environment, it doesn't mean that they're repeatedly associated there. And so you need to have some flexibility for those outlier situations. And so CMECS wants to be able to provide that flexibility for people. And a good example of this came up, again, I was contacted by a colleague through the ESIP partnership who was having issues with almost exactly that situation. So everybody, I hope, knows about the OBIS database, the Ocean Biodiversity Information System. And they rely on Darwin Core and EML to metadata standards to document their records. And he was trying to represent some habitat information in the metadata of some observations. And so in OBIS, in order to maintain FAIR principles, they recommend using controlled vocabularies with machine interoperable identifiers, such as those that the JNCC and the BODC vocabulary server provide. But however, the JNCC biotopes weren't giving him the exact description that he needed for the samples that he had. And so he didn't want to, include information that wasn't actually there, which you would have to do if you were using, a strict biotope definition. And so he reached out to me to see if CMECS had like other terms that he could use. And so we talked about it, and yes, it seemed like we did. And so the timing of this was actually really well because, speaking with the team at OBIS, they said, well, we're aware of CMECS, but we're not sure that we really want to use it because, CMECS isn't machine accessible. Like you don't have like a web page where you can go and access each individual term. And I was like, oh, okay, well, we've been working on this digital transformation and we're like really close, and I think that we have it. So, he was able to move forward and use the CMECS terms and give a much more accurate description of what was actually in the data that he could present in that sample at the time. And so I think that, details like these are really important and be able to generate accurate scientific information. And so this sort of connection and, applicability is worth exploring further. And that's something that I would like to take a deeper dive into, looking at exactly what information like OBIS wants, and also to look at how OBIS samples that do have habitat information can then sort of be like mapped out, not just with the occurrence of the biota, but also the environment, and sort of develop an interactive environment map with that. And so now I've mentioned the need for the interoperability and the machine actionable resource. And also I'll just touch really briefly on this part of the standardization and the update, right? So I mentioned that we had been making scientific content updates to CMECS. And so we have a proposal or a process that people use to submit changes. This diagram here just sort of shows like the pathway that a proposal might take. The simplest pathway is shown in blue. And so that could be like, if you found like typographic error, spelling, grammar, or we need to clarify some meaning in something, these are pretty simple changes that just need to be discussed and can then be made. They don't have any impact on existing work. This could also include the adoption of provisional units. So if you are working on something and you have a need for a unit that is not in CMECS, but it sort of fits in there, and it seems like perhaps like other people you'd like to propose to have it added to CMECS, you can use that unit in your work and call it provisional while it's going through this process of review and adoption. And so this process is overseen by the CMECS implementation group. And so we've run through this with, we've started with this on the substrate component and completed it with substrate. We're working also on the biotic component and the geoform component as well. Those are in progress. And so once we make those changes, CMECS has previously just existed in the format of like the standard document. It's like 300 pages long, and it has like all the scientific context, as well as the whole listing of the units and the definitions and so forth. So we had that. There was also a Microsoft Access like CMECS catalog database that had all the terms and the definitions in it, and a relational database. But as we were going through the changes, we knew that we needed to sort of update this resource. And the solution was to transform it into a fair vocabulary. And if anybody's interested in this, I'd recommend checking out this publication, The 10 Simple Rules for Making a Vocabulary Fair, because they lay it out very, very easily. And so we needed to do this because we wanted to preserve all the original and subsequent versions for reference and comparison throughout the whole life cycle of CMECS. And so we needed to sort of like create this a digital resource that we could like update easily and be able to provide authoritative and verifiable resources that are easy to cite. And we wanted the resource that we ended up with to be machine readable and machine actionable. And so it's easy to access and use, and can be, transformed into multiple formats and for different purposes. And so I think I mentioned earlier that we transformed that Microsoft Access database into an ontological web language file. So it's CMECS OWL, so it's an ontology. So we still have the original CMECS document that has a whole lot of information in it that is not contained in simply, the terms and definitions. So that's archived with the NOAA Institutional Repository. But then we're managing the CMECS OWL file in a GitHub. And so that's the CMECS catalog. And so, we not only distribute the OWL file from there if people want to take that and use it for other purposes, but then we also have like an updated like CMECS thesaurus. So that's where you'll find the most recent list, most up-to-date list of all the terms and definitions. And then we output some tables because these are helpful for people to use in their work as well. And we always give like a summary of files and a list of the changes as we make different releases. So that GitHub,
Hey, Kate,
yes.
I'm sorry. This is fascinating. And I just wanted to say we have approximately 3 minutes left in
Yeah.
our webinar. And
Oh,
I'm sorry to interrupt you. I just trying to do a gentle time check here. Maybe we could start to move towards questions.
yeah, I will. Sorry, I was looking at a timer. I saw 50 minutes, so that's the wrong timer to look at, though. Okay. So I'll move on from that. But so basically, now you can also view CMEX with these individual IRI links that OBIS really likes to have, and other metadata providers and generators like to have, to be able to include CMEX terms digitally in their records. So, which is already like a great step forward and a great validation for doing this. This also, allows us, provides some API capabilities, and so we're excited to see where this goes. And so then my final slide was to end on, when we were first applying to join the Marine Life 2030, Frank had asked me like where CMEX could sort of help with, further enhancing and developing the IUCN global typologies. So we haven't had a chance to really dig into that too much, but obviously CMEX contains CMEX classified data sets that exist already, contain a lot of information that could help identify, the ecological traits and key ecological drivers that kind of go into then defining these the various ecosystems. And so that's actually where I was going to end right there, and say thank you to everybody at Marine Life 2030 and the Ocean Decade, also to our partners at ESIP and the people that we spoke with at OBIS, and everyone in the CMEX implementation group who's been working with us there. Sorry for
Thank you,
taking
Kate.
so long, but yeah.
No, it's a lot of information and very fascinating. Thank you for sharing all of that today. I'll go through it. We have a couple questions in the panel here, and I'll just go through in the order they came in. And so we were or Jonathan was wondering if CMEX has a way to identify the paleo landscape features like submerged cypress forests.
There's probably like a combination of units that you would use for that. And it sounds like, if I'm thinking about like paleoforests, the ones that I sort of envision that we have here on the Gulf Coast as well would be a combination of probably different substrate units, where you would use some of the geologic origins, so to describe the mineral substrates, that then you would have a biogenic substrate. Within that biogenic substrate classification, we do have a bunch of different units for wood, whether it's like trees or branches or root balls and things like that. So we do have those descriptors that you could use there, and you would probably be using those in combination. Yes.
Thank you. This next question comes in from Frank regarding the CMECS. It seems more comprehensive and detailed than the marine elements in the IUCN habitat classification scheme. And yet the IUCN scheme is basically adopted widely for biodiversity work internationally and highlighted in the framework. If it's not already, can CMECS and IUCN work together to provide a standardized habitat classification for ecological work globally, or is it best taken care of working through vocabularies like ENVO?
That's a really good question, and I'm not really sure. And so I feel like, I've been involved in seeing, like, through various like meetings and conferences, just there is a desire to have like one classification and one vocabulary, but also, and that does sort of provide that standardization that's great, but it's I think it would take a lot of iterative work to get there, and so that would be a lot of collaboration between IUCN and ENVO and CMEX, and the other classification standards as well, to sort of like look and see and do a lot of comparing and contrasting and see how they what they have in common, right? And so this is sort of like the harmonization work that we had been looking at with ENVO, and just kind of, we've just kind of gotten started on that a little bit. CMEX organizes data in a different way than ENVO does. ENVO organizes their data in logic, in conceptual logic, sort of hierarchy, where they look at a material and then a type of material, and so CMEX is a little bit different because it is so closely tied to the mapping and the spatial aspects of it. And so CMEX is probably a bit more of like what we would call like instead of being like a general domain ontology, it is more of like a project ontology. So it's developed for a specific purpose. And so I think that each of them have, and I, to be honest, have not looked into IUCN closely enough to sort of see how we could begin to approach that, but it's definitely something that that I'm interested in looking at. But I think it's going to end up, I don't know, perhaps having a few separate resources that do different things, but that people are able to use and customize for certain purposes. Just because it's
Okay.
so, environment's so complex. Yeah.
Alrighty, thank you. We're a few minutes after the hour now, but if you have the time, I'll keep going with just a couple more questions.
Yeah.
And this one's also from Frank, and it's to me and you. And he's wondering if habitat classifications like CMEX could be linked to resources like Protected Seas Navigator, and would that be useful? And we haven't had the chance to delve into this conversation too much, but the Protected Seas Navigator tool, like I've mentioned, has global regulations as well as level of fishing protection scores for globally in 200 countries. And so if scientists were curious both about a level of fishing protection score and then also the benthos, that could be interesting. We've done integrations with other tools. I'm not sure we can talk about this more perhaps offline, but Kate, what are your initial thoughts?
Yeah, I took a quick look at the tool after we spoke the other day, Deirdre, and and I feel like this happens, I think, with CMEX a lot, where if you have habitat information, or embed those information in already in your application. That information may have already been classified with CMECS, but you just kind of don't know, because it's sort of like, just this sort of like it's a tool that you use, but it's not really, out there. It's not like it's a CMECS, so um, yeah, but something to look at a little bit more. I think that I would say that whatever end product that you're using might already or could be, classified with CMECS. It just kind of depends on where you're getting your data from, and what purpose, what you want to show with it.
Alrighty, thank you. So the next question, when introducing the semantic resource, you mentioned that CMEX classification was based on systems like Wentworth and Folk. Did you use established systems, and did any of them disagree with each other? For example, differing definitions of the same terms? And if so, how did you address these discrepancies? By sticking to one system, surveying usage, or finding a compromise?
Um, so is that talking about like the original, talking about the semantic harmonization work specifically,
Um,
or
I'm
yeah,
not sure if
I catch that
Reyesa
first
is
part of the question.
still, yeah, if Reyesa is still on the call, and I know a few people are dropping off now, um, but perhaps we can get their contact information and reply uh, through email or something.
Yeah. So if we're uh, developing the ontology, we, I mean, I guess I don't really know like the absolute details of when they were developing the subject classification for CMEX itself, but there was a lot of back and forth um, with all of those, participants and the authoring group, and that to sort of like work those out. And so I can't really like speak to what those discussions were. Um, but if the question was more about like, the harmonization work that we're doing now, I think that that's kind of in progress. And yes, there are discrepancies, just really in the way that we, in what our terms um, describe, sort of like the basic concept of the CMEX terms compared with the basic concepts of the ENVO terms. So, yeah.
All right. Thank you. And I guess let's just leave on this question of you've shared a lot, and in looking towards the future of this project, what are your next steps?
I think the next steps are, we obviously want to continue and get through this this comprehensive review of CMEX, of the content, and so as we're doing that, I'm also refining the CMEX OWL file to sort of like add in, bits of like guidance um, and things like that, and more context notes that provide a little bit like of guidance to the user about like, oh, you might do this, and to also sort of develop more like axioms and rules between the different units and the modifiers that are also going to be helpful for people in using the classification. So that's something that we want to do, but also to continue looking into, now that we have this digital resource, and now that we're in this world with artificial intelligence and large language models and machine learning, um, you know, what does that open up for us, and how can we perhaps automate sort of like classifications of data so that we can have like different so that we can experiment and see what does work best as far as like aggregating data and pulling it all together, into these like regional or global products, and how that works. And so that's a very like exciting but also huge uh, subject to tackle. But I think that's going to be where it's going. So
Okay, thank you, Kate. This has been, like I said, a fascinating presentation, and we should probably wrap it up since we're 9 minutes after
yeah,
the hour, and let people get on to the rest of their Friday
yeah.
mornings, afternoons, evenings. Thank you so much for all of your efforts and for conveying this information.
Thank you very much. Have a good day,
And
everybody.
with that said, yeah, have a good day. Bye.
Thank you. Thank you very much to you both.
Yeah, sorry I went on so long. I'm like, going into this, I'm like, I never get to talk for an hour. There's no way. I thought I would be like a half an hour, but I don't know.
Yeah, I'm
So
sorry. I hope that wasn't too interruptive.